Hello. So, today we are going to take a little bit abstract view of our string matching problem. Recall that we used to have a text string A1, A2, AN. Now, in place of a patterned string, I am going to have a regular expression R. Now, you must be familiar with a regular expression. This is equivalent to regular languages. Every regular language has a corresponding regular expression, and vice versa. Our problem now is to determine whether there exists some index I such that starting from AI there exists a string, a substring of T starting at AI, which belongs to the language of R. Now, we know normally that there is an automaton we can build from a regular expression, and then we can input the string starting from location I and see if we reach the final state. That would be a simple answer to this. But we also know that in general the number of states may be exponential in the size of R if we want to design a deterministic automaton, and that would not be very efficient. So, what our goal is that we design a non-deterministic finite state automaton in a suitable way, such that searching for a member starting at AI in the language can be done in polynomial time. So, what I am going to do first is devise an algorithm for a specific task in the context of graphs, and then we move on to design an automaton and solve the problem. So, right now my problem moves to a issue in a graph. We have a directed graph G. G and the vertices of V are either unlabeled or they are labeled from a set of labels sigma. So, we are partly labeled by symbols of sigma. Now, our task is to compute the following function. Let us denote that by f. S and a label L. Now, S is a subset of V, set of some of the vertices. L is a specific label, belongs to sigma. I would like to compute some of the states or some of the vertices of the graph which are given by the following. So, I would like to compute a vertex, the set of vertices would be y, where there is a path from x, x1, xk, y is a path in G, x belongs to S. So, this is a path that begins at some vertex in S. Further, we want that all of these vertices x1 through xk, they have no label. So, label of xi is nil for I between 1 and k minus 1 up to this point. Further, the label of x k is L. So, we begin at some vertex of S, we walk along unlabeled vertices, of course, this is a directed path, until we hit a vertex which has label L, and then the following that there is some vertex to which it can go from x to y. Such vertices are what we want to compute. Now, to compute such vertices, we effectively can initiate a search process starting with this set of vertices. Now, recall that in a search process such as depth first or breadth first search, what we did was we began with a vertex, say S, small s, and we went along the edges wherever it took us, and then those vertices. So, we had an S here and it went to say some of these vertices, say x1, x2, x3. What we did at that time is we saved these vertices in a data structure. In one case it was a stack, another case it was a queue. Now, it is not important what data structure here we use, but we save them, and then we pick a vertex from that data structure and then proceed the expansion, so resume the expansion from these points. So, we will continue to do that. In the meantime, that data structure has several vertices. Those are the vertices from where we have yet to perform the expansion. So, we have essentially done a similar kind of search. What we will do is, we will continue to expand as long as the vertex has no label, because that is what this says effectively, until we hit a vertex with label L. If we hit a vertex with another label, we will terminate that path. If we hit upon a vertex with label L, then the following vertices, everything that we can reach, will be all valid members of this set. So, let us just capture that in this algorithm. So, let us say we have f to which we are given a subset of vertices S and a label L. I am going to use two data structures. One, in fact, both of them are arrays of Boolean value. For each t in V, we will set Bt to be false and Ct also to be false. What this indicates is that this vertex has not yet been incorporated into the data structure from where we are going to pick vertices and expand, and Ct says that T has not yet been output into this collection, has not been. We do not want to duplicate these efforts, that is why we are using such Boolean arrays. Now, so far we have initialized to empty, but we also know that to begin with we will put all these, in fact we will use the same set S as the data structure into which vertices will go for expansion. So, initially the value of S is this S itself. So, I am not going to use a new data structure, but say for each T in V in S, in S, we will set B to be true. So, all of these have been accepted for expansion, because we are going to start, we are supposed to start at any vertex in S. So, all of them are put into S. Next, we are going to continue the expansion until S becomes empty. So, we will say while S is not empty, do. We will pick a vertex from S, we will look at its label. If the label is nil, then we will look at its neighbor and decide whether they should be put back into S for further expansion. And if the label is L, then we will decide the adjacent vertices should be put into the data structure S prime, the final output set. I will call this set S prime. So, I will decide to put that into S prime. So, let us just do that. So, let us say we have U pop from S. By this I mean I am extracting one vertex, any vertex from S, and removing it from S, and then check if label of U is nil. Okay, so all right, then so I am going to resume from here. In that case, then we are going to look at all the neighbors for each V in the out adjacency, which this is a directed graph. So, every vertex to which there is an arrow from U. So, I will say out adjacency of U. If V has already been incorporated in S and has been either expanded or waiting for being expanded, we do not have to do anything. So, we will say if B of V is false, that is to say it has not yet been approached for expansion. So, now we have found it, we are going to then put this vertex in S, and we will set B value of this vertex to be true. So, future expansion will be possible from S. Now, this was if the label was nil. Now, else if the label of U, now the next thing we are going to check is if the label is L. In that case, I should have initialized a set S prime to be empty, because this is where I am going to put my output. In that case, we will again look at all the neighbors for each V in the out adjacency of U. We do the similar thing, but this time I am going to output that vertex. So, if C of V is false, which means V has not yet been output, but please note that we have found a path starting from some vertex of original S, where all the subsequent vertices had label nil until we hit U, which had label L, and then we have neighbor of U, V, which should be put into that set. So, we are setting then S prime is S prime union V, and we record this fact in the array V by setting this to true. And that is about all. So, this is where the process will terminate, and finally, we will output, we will return S prime. Now, once you see that this is exactly what this algorithm computes, and you notice that this is really the same process of search that we have seen in both depth first and breadth first and all, the cost can be very easily determined. We never expand the same vertex second time. Once a vertex enters S, it is eligible for expansion. Once it is expanded, in fact, the moment we have taken it into S, we have set this to true, this Boolean value to true. So, second time, we have checked whether it is false. So, that will no longer be true second time. Hence, you will never expand the same vertex again. And the starting from a vertex U, we are looking at its neighbors V1, V2, V3 and so on. Since we are not going to expand again, we are not going to visit this edge again. So, each edge can be visited at most once. And we may not have any edges, and we may have all the vertices in S. So, we have to actually initiate the process from every vertex in S. Hence, the total cost, the time complexity will be order M plus V, where M is the number of edges, and this is number of vertices. We also ensure that no vertex is put into output set S prime more than once by using this array CV. So, we are not going to duplicate any effort. So, suppose we have a vertex V which can be approached from U1 as well as U2. When we were expanding U1, we reached here and it was eligible. So, because this had label L, so had this one. This was eligible to be put in S prime, so we did it. Second time, when we come here, this cost goes to this edge, but then we are not going to, we will find that the label is false, the C label is false, hence we are not going to put this again into the array S prime. So, no duplication, and hence this is very easy to see. The total cost is linear in the vertices and the edges of the graph. So, now let us come back to our original problem of matching a string with the language given by a regular expression. Now, what we will do is we will specify a certain way of designing a non-deterministic automaton for R. Then we will relate the cost of search in that with the problem that we have just solved. So let us just build an NFA for R. You notice that there are three basic operations. Okay, the operations are the plus, the catenation, and clean star. These are the three operations you have. So we will describe this building process in a recursive fashion. So if R is simply a single symbol A, then the automaton we are going to design will have one state here A, and then we will keep a separate state which will be our final state. And of course, this arrow indicates the start state is this. So this will take care of this regular expression. There is only the string containing A, one single string that this recognizes. Now suppose we have two regular expression R1 and R2. Let us symbolize the corresponding automata as well, I will just indicate that this is my automaton N1, this is its start state, and this is indicating that there may be several edges going from this part of the structure to this state, which is the final state of N1. Similarly, I have this is N1 is for R1. Similarly, you have automaton here we have N2 which accepts the words of R2. Given these two, I am going to now put together an automaton for R1 plus R2. Note that this is the union of the language of R1 and R2. So we must be able to accept any string that is acceptable by either of the two. Okay. So I am going to have a state, new state to indicate the start state, and then we will have an arrow so this is actually original N1. And then I have, since it is a non-deterministic automaton, you can have edge, another edge, so we have this would have been N2. What we have done is we merged their final states into a single state. We have created a new state for a start state. You can start from here and either way you can move, and once you go there without spending any symbol you can move here and then you go there. Notice that our requirement is that when you hit a labeled state, at that time you must spend one symbol of this label to move forward. So if my string is just A, then even if there were some other states without label, I can proceed. But the moment I hit here, I can only move forward if I have A in the input. This is our requirement. So, suppose this was very simple, simply a single state with label A, and this was a single state with label B. Then I would have moved from here, and if I had a string containing just A, then it would have allowed me to move on to the final state. If I had simply B, then this will not allow, but this will. So, this makes the union of the two languages. How about concatenation of the two languages? This is the set of words where you can, each word is catenation of a word from R1 and a word from R2. So, this will essentially be the same R1 automaton earlier there was a final state. We will replace that and directly put the automaton for R2. And then we will let this go to state F. So, if you notice, this is exactly the automaton of R2, and if you treat this as final state, then this would have been the automaton for R1. So, we have just put them together. It is again very easy to see. Okay. Here is the start state, we should indicate that. If there was initial substring in my input belonging to the language of R1, then there was a way to reach here at the end of that. And here I can begin the second part where I had a string of R2, then I would reach the final state. The last one is a clean closure, and to compute automaton for R1 star, we are going to take the automaton for R1. Now, earlier I had the final state for R1. Instead of that, I am going to introduce a new state. I will introduce a new state and then let it go to the final state F. And then we will have this as our start state. But this will also have one way to go to the original start state of R1. Now, notice that if I start, I can immediately move into this with empty string, because empty string is in the closure. Else I will just move here, and after one string of R1 I will reach back to this. I can either go there or resume. So, you notice that these are the steps to construct our non-deterministic finite state automaton for any regular expression R. All right. So, once we have defined all the constituent steps, we can now build the automaton for any regular expression. Now, at the end, once we have built an automaton for R, symbolically stated, looks like this. We will just make one more addition to this, and that will be that we will invent a new symbol, a special symbol, and associate that with the so called final state, and then attach to this the state which will be actual final state. And now I am going to claim, the claim is that any string L1, L2, Lk belongs to the language of R if and only if, starting with the start symbol. So, I will call this state S. So, I start with S, search for all the states which pass through L1, and then proceed with this set of states. I go beyond L2 and go on, and finally, I will have Lk. Now, that will allow me to go past the last state, and then ultimately I must be seeking this symbol, because this is the symbol of final state. So, at last I will do this. If I do this and I still have some state left, that means I have managed to reach the final state. So, this should be non-empty. That is the complete characterization of the membership of this string into the language of R. Now, to justify this, I will not give any formal argument, but just to justify this, let us just take a look at let us say a small example. Suppose I have a start state and I have a state with label L1, maybe then I have state with label L2, a state here, maybe similarly then the application of F on state S with L1 will allow me to reach this state, because we have just crossed L. It will allow, will go this way will terminate because we just find L2 directly. This path will also find this. Maybe we may have another state here. So, we will reach this state and this state. Then if I apply F on this set of states, which is this and this with L2, then I will find that L2 matches right from the beginning. We have a state matching with our desired symbol, and I will jump to this state. Let us say this is not labeled with L2. So, this will continue. If there is any further path, it will resume the search. So, what will happen? Let us come back to this automaton, that ultimately I will reach a state, if indeed this was in the language, I will reach a state in this automaton from where there is a epsilon path, unlabeled path of arbitrary length to this state, because this was the original final state. The last application with respect to the sharp symbol will go reach here and jump, finally output this state as the value of this expression. That means that if this is non-empty, means I have reached here. That would mean there was indeed a path through these labels and empty symbols in between, which took me to the final state. Hence, if this is true, the symbol, this word is indeed in the language of the automaton, and conversely. So, the search cost for any given string of length k will be k plus 1 applications of f. So, the routine that we had written will be run k plus 1 times on this automaton. Okay. So, now the time complexity will be, if I start the search starting from each xi, then will be I equal to 1 to n, that will be n minus I plus 2 m plus v. So, let us now try to decide the value of m and v. For this, we have to go back and see how we have built our automaton. So, for a single symbol, the automaton looked like for each symbol we will generate 2 states and 1 edge. So, let me now assume let R have L1 symbols. So, by symbols I mean total with multiplicity the total occurrences of all the symbols. So, if there are 2 occurrences of A, it will be contributing 2 to L1. L1 symbols with multiplicity. We have L2 OR symbols, L3 concatenation and L4 closure symbols. So, we will estimate our edges and vertices, which is V. We get 2L contribution, L1 contribution and L1 contribution due to the symbols themselves. Then we have OR operation. In that, what we did is we made a new state here and we had a so whatever these automata already had, that we do not have to account for, but we have created a new state here and we have merged 2 states here. So, we have not created any additional state in this case. So, the number of states will be nil and number of edges that we have created will be 1 and 2 more. So, 2 L2 edges due to the OR operation or plus operation. The catenation so whatever be the number of edges going there, we have the final state here. This was our final there. In this case, once again the final state of the first automaton has been removed and we have used this as the replace that final state by this state, and the final state of the second automaton is here. So, no states here. And we do not have any new edges either. There are no new edges in this construction. So, we have 0 edges, and the closure was built in the following fashion. We had this was the original automaton. So, we have added one more state. We have added one more edge here and one edge here. So, two edges, that will mean 2 L4 and 1 L4 here. So, M plus V is less than equal to 3 L1 plus L2 plus L3 plus L4. And notice that the symbol, the expression for R, its complexity is L1 plus L2 plus L3 plus L4. This is the total number of symbols in it. So, we can write this as 3 the complexity of R. So, the time complexity becomes will be order n 3R, searching from any one symbol. But if you are going to search from each I, then this will be order n square mod R. This will be the total cost for searching for any string of the language of R, whether any contiguous string belongs to the language of R. Well, this is actually polynomial. You notice that we used to have a brute force algorithm for simple pattern and text string was n times m. If we think of this as the length of the pattern string, then this is n square m. But notice that here we are able to search the entire language generated by R. Okay, so this is where we complete the discussion of pattern matching, and will begin with a new topic in the next class.